Okay, in this video we're going to be looking at a family of functions called power functions. And you can see up at the top of your notes you've got 5 different functions that you're told are power functions and 2 other functions that you're told are not power functions. Now in just a minute we're going to be looking at the definition of a power function and look at some certain characteristics of power functions. Before we do that, however, I want to ask you to take a look at these 5 functions here that you're told are power functions, and also these that you're told are not power functions. And I want you to see if you can come up with something that makes these functions power functions and that makes these functions not power functions. In particular, there's 2 things that I think you could probably figure out, 2 things that are true about power functions just based on this set of power functions and this set of functions that are not power functions. So what I want you to do is pause the video right here, take about 30 seconds or so, look at these power functions and the functions that are not power functions, see if you can come up with what might go into these blanks right here. And then after you do that for about 30 seconds, unpause the video and come back and we'll take a look at them. So go ahead and pause the video right here. Okay, so welcome back. Either you pause the video and you tried it for yourself, or you're just saying, just go ahead and tell me what it is. So one of the things that's true about power functions that is not true about other types of functions, power functions only have one term. That is, power functions are always what are called monomials. And you can see each one of these functions here, there's only a single term. All right? In this function down here, which is not a power function, it has 2 terms. That's what makes this function here not a power function. All right? Now, something else that's true about power functions is you'll notice that each one of these functions, they have a variable with an exponent. All right? Variable, that's an exponent of 1. This one you may look at it and think, wait a minute, this variable doesn't have an exponent. Actually, it does, because you can rewrite this one as x to the 1/2 power. So we have variables that have an exponent, but notice that all of the parts of the power functions, a power function cannot have a variable in the exponent. So in other words, for all of these exponents that you see, you've got x to a power, x to a power, x to a power, x to a power. In none of the power functions is the variable x in the exponent. And that's a particular characteristic of power functions. So let's go ahead and define what a power function is. A power function is a function that has the form y equals k times x to the power of p, where k and p are constants and k and p can be positive, negative, or fractions. So example 1 here, it says, which of the following functions are power functions? If it is a power function, state the value of k and p, and if it is not a power function, explain why. So let's take a look at each one of these functions. Here I've got the function 13 times the cube root of x. I can see that this is just one term, and I can also see that it's got a cube root, that is, it's got a root symbol in it. Let me rewrite this in a form where I'm using, instead of a root symbol, I want to rewrite it in a form in which I'm using a fractional exponent. And I know that I can write, anytime I've got a variable under a radical sign, I can rewrite that as the variable, the part under the radical sign. This is x to the 1st power. I can rewrite this as x to the power of this over this. In other words, x to the power of 1/3 is the same thing as the cube root of x. Well, now I can identify this. I can see that, in fact, this is a power function. And I can see, so let me just say, yes, it's a power function. K equals this coefficient here in front of the variable. K equals 13, and P equals 1/3. In other words, it fits this form, y equals k times x to the power of p. K is 13, p is 1/3. Example 1b. Is this a power function? Well, it looks like this is going to be a function that has more than one term. So I suspect this is not going to be a power function. However, let me go ahead and multiply out, get rid of my parentheses so I can see if in fact this is going to be more than one term. 2 times x plus 5 squared means 2 times x plus 5 times x plus 5. I'm going to use my FOIL method here to multiply this out. So that's going to give me 2 times x squared, 5x, and 5x is 10x. 5 times 5 is 25. Now I need to multiply 2, use my distributive property and multiply 2 through here. So that's going to give me 2x squared plus 20x plus 50. And now I can see that, yes, I have a function here that has 3 terms. It's trinomial, so no, this is not a power function. I'm going to just say no, it has too many terms. It's not a monomial. All right, now in this one, I've got a very similar situation. I've got 2 binomials multiplied together here. And at first glance, I would look at this and say, well, no, that's not going to be a power function either because it's going to have more than one term. However, I'm going to do the same thing that I did up here, which is I'm going to go ahead and multiply this out so I can get rid of my parentheses and see what this is going to look like after I multiply that out. So once again, I'm going to use my FOIL method and multiply my 2 binomials together here. So let's see, that's going to give me x squared. And let's see, my outer terms, that's going to be negative 3x, positive 3x, positive 3 times negative 3, that's negative 9. This is plus 9. And now you can see what's about to happen here. My 2 terms here, negative 3x and positive 3x, they're going to both go away. I've got a negative 9 here, which came from multiplying my 2 binomials, and then I've got a positive 9 here, which was added on at the end. These 2 terms are going to go away. And what I'm left with is just an x squared term. So yes, this is a power function. K is equal to 1. That's the coefficient of my x squared term. And P is equal to 2. All right, how about example 1D? Is this function a power function? Well, again, since I've got this radical sign in there, it's kind of hard to tell what, 1, if it's a power function, and 2, what K and P are going to be. So let me see if I can maybe simplify this, write this in a slightly different form. So first let me write this as square root of 25 over the square root of x cubed. Now I know the square root of 25 is 5, so I can get rid of that radical sign. The square root of x cubed, just like up here, when I change this radical symbol into a variable with a fractional exponent, I want to rewrite this using fractional exponents. So the square root of x cubed, and remember, anytime there's a square root symbol, if there's no number there, there's kind of an implied 2 there for the square root. So the square root of x cubed I can rewrite using fractional exponents as x to the power of 3/2. And now I remember that anytime I've got in the denominator, if I have a variable with a fractional exponent in the denominator, I can put it up in the numerator as long as I take the negative of the exponent. So I can rewrite this as 5 times x to the negative 3/2 power. And now I can see that, yes, this is a power function, and I can also see what K and P are going to be. So yes, this is a power function. K equals 5. P equals negative 3/2. And finally, my last one, this one I know right away is not going to be a power function because I've got a variable in the exponent. And I cannot have a variable in the exponent for a power function. Okay, examples 2 and 3. It says, below are the graphs of 2 power functions. Which graph would match the power function f of x equals 3x to the 4th, and which would match the power function g of x equals negative 2 times x to the 7th? Well, this one is not too hard to figure out using your graphing calculator. If you take your graphing calculator and you just enter these two functions in and graph them, then you can see pretty quickly that the function f of x equals 3x to the fourth power is going to correspond to this orange colored function here. So this is going to be f of x equals 3x to the fourth. And if you enter the other function into your graphing calculator, then you'll see that g of x, which is negative 2 times x to the 7, that will give you a graph that looks like this green function here. So that's not too difficult. The more interesting question is part B here. It says, name two other power functions which would also match the shape of these two graphs. Now notice, I'm not saying what are two other functions that would look identical to the graph of 3x to the fourth or would look identical to the graph of negative 2x to the seventh power. I'm saying what would be two other power functions that would have a graph whose shape is similar to this U shape here, or whose shape is similar to this kind of chair-shaped graph, all right? And so you know what a power function is. You know that it's a function that's in this form, y equals k times x to the power p. I want you to use your graphing calculator and play around with the k value and the p value. See if you can come up with two other functions, one that has a similar U shape like this one, and another one that has a similar chair shape like this one. I'm going to leave that one for you to do. We'll take a look at that one in class tomorrow. Meanwhile, example number 3 has another similar type of problem. It says below are the graphs of two power functions. Which graph would match the power function f of x equals x to the 1/2 power, and which matches the power function g of x equals x to the 1/8 power? Again, using your graphing calculator, it's not difficult to plug in these two functions and figure out that this function is going to match f of x equals x to the 1/2 power. And this function, which looks very similar except it's kind of squashed in a little bit more up against the y-axis, this function matches f of x equals x to the 1/8 power. All right, so again, that's just a matter of plugging those values into your graphing calculator and see which picture on your graphing calculator matches these graphs. Again, however, you've got part B, name two other power functions which would also match the shape of these two graphs. And again, I'm going to leave that one to you, and we'll take a look at this in class tomorrow.